Today we're going to talk about lesson 4 in unit 4, chemical bonding, which is on VSEPR theory. And if you could look at the first slide here, it says VSEPR stands for the valence shell electron pair repulsion theory. And basically what it is a way of explaining the shapes that molecules will take based on the arrangement of their electron pairs around a central atom. So if you read the definition for VSEPR theory, it says a theory that predicts the molecular shapes based on the ideas that pairs of valence electrons, because they're all negative, will surround an atom and repel each other. And as a result, they will try and get as far away from each other as possible. So as we go through this slideshow, my first recommendation to you is that you open up your own VSEPR theory guide that you're going to submit for credit and try and complete it as we go through this together. So looking at the first one, we're going to base all of this on our Lewis structures that we completed last week. So when we learned about Lewis structures, we saw electron domains, which were areas around the central atom where electrons are found, and bonding domains. So out of those electron domains, which one of those were bonds? So this week, we're going to take those numbers and basically identify what the name and shape of these different molecules will be once we account for their electron domain and molecular geometry. So as we go through this slideshow, I'm encouraging you to open up your VSEPR theory guide assignment and complete the assignment as we watch this video. If you need to, just pause the video so that you can catch up with anything that we've completed on the screen. Now, we're going to start off by looking at the number of electron domains and bonding domains. Those two numbers are going to tell us what shape this molecule will take. Now, in the name of geometry column, I have two abbreviations here. So I'm just going to spell this out for the first example, but we're not going to list this each time. So EDG stands for electron domain geometry. And this is the arrangement of electron pairs around the central atom. Remember that when we're talking about the shape these molecules take, we are only concerned about the arrangement of electron pairs around the central atom. So none of the other electron domains count on outside atoms. The second abbreviation here is molecular geometry, which may be different depending on the two numbers that we find here on the left side. So in our first example here, the electron domain geometry and the molecular geometry will be the same name. And in fact, that will be true anytime both numbers are the same. So we're going to put in linear for both of these. Now I'm going to arrange my atoms to depict for you what the molecular geometry will look like. But before I do that, I want to show you a three-dimensional representation of what this looks like. So I'm going to click to this tab here. And if you notice, down here, I have molecular geometry linear, electron geometry linear, and if I move this around, you can see what this looks like in three-dimensional space. So we have a single atom in the center, that's our central atom, the purple atom, and then we have these two gray atoms on the outside, and you could see, regardless of how you twist this, you could see the shape is just linear. All three of these are in a line. So now going back to our VSEPR theory page, I'm going to arrange these atoms so that they look like the model represented. Okay, you can now see what our molecular geometry representation looks like. And then in the last column, we will fill in the bond angle. In this case, there's a 180-degree bond angle. There is only one of them. So in parentheses, we will put a 1. Some people argue that there might be two, but there's really only one because you can only look at unique bonds. So BAB, this 180-degree bond angle that we see right here, is the same one that we would see down here. If we look at our second example, in this case we have 3 electron domains, all 3 of which are bonding domains. So this is going to get the name trigonal planar. And the molecular geometry, again, because both of them are 3, will take the same name. So this will be trigonal planar. So trigonal or trigonal means that it looks like a triangle. And planar because all of the atoms are in the same plane. So if we look at this representation, You can see what we have here. And if you hold this just the right way, you can identify that all 4 of these atoms are coplanar. They're all in the same plane. So our picture is going to look like this. So I'm now going to rearrange these atoms so that it looks like the picture that we saw in 3-dimensional space. So you can see the picture in 3-dimensional space. Your pictures do not have to be perfect. You'll see as we go on, mine are going to look far from perfect. In this case, we have 3 bond angles. So we have a bond angle here, we have a bond angle to the right side, and then of course we have our bond angle at the bottom. If you think about a full circle being 360 degrees, we have 3 bond angles that are equivalent, so each of these is going to be 120 degrees. So I'm going to list 120 degrees and put a 3 there. In our next example, we have 3 electron domains, so that will get the same name as we had before. In fact, everything with 3 electron domains will get called trigonal planar. However, in this case, the molecular geometry is going to be called bent, and you'll see why when we look at our 3-dimensional drawing. So the names of the molecular geometry are based on the arrangement of atoms, not necessarily the factoring in the pairs of electrons here. So if you notice, this kind of looks like a straight line that was bent a little bit. So in this case, we call the shape bent. You can see that they are still coplanar, all 3 of them, including the pair of unbonded electrons that are at the top there. So we're going to do our best to try and recreate this. So I'm going to do this so that we have our pair of electrons coming out on the left side. In this case, the pair of electrons that is unbonded, that is coming off on the lower left, actually causes the bond angle to shrink slightly. It's compressed. So now we have a single bond angle of about 118 degrees. So we went from 3 different bond angles to now just 1, because remember, bond angles cannot include a pair of electrons. So the only bond angle that we have is between the B, A, and B here. In our next example, we will look at a tetrahedral molecule. A tetrahedral molecule is going to have 4 electron domains, all 4 of which are bonding. So we can add the name tetrahedral to each of these. And when we look at our 3-dimensional drawing, you'll see that all of our bond angles are the same. So we have one pointing up, we have one pointing down and to the left. Now this part is a little difficult to see, so I'm just going to turn it a little bit. We have one coming out of the plane toward us. We have one back behind the plane. Now, believe it or not, all of the bond angles are exactly the same. So if you notice, regardless of how I twist this, if I put one up toward the top, it looks exactly the same, regardless of which one I put up at the top here. And it turns out that these bond angles are 109.5 degrees. Now in the past, the bond angles are really kind of easy to see. In this case, I'm going to show them to you. So if you notice, even as I turn this, that 109.5 degree bond angle is the same all the way across the board there. Okay, so let's go back and arrange our atoms so they try and look like that as much as possible. Now, this is the first time that we've had to draw something in 3-dimensional space. So I'm going to use this wedge, this black wedge, to represent the atom that's coming out of the plane of your screen toward you. And I'm going to represent this gray wedge with the atom that is back behind the plane of the screen. So this is what our tetrahedral molecule will look like. As I mentioned earlier, the bond angles in this case are 109.5 degrees. And if you look, we have 6 of those. So the top one with each of the B's that are down here, that's 3. And then each of these B's through the A with each other. It's the other 3 for a total of 6. In our next example, again, we have 4 electron domains. So again, at the top here, we're going to include the term tetrahedral. But this time, because one of those is not bonded, it gets a slightly different name. So if you look at this drawing, you'll notice that the name down on the bottom here becomes trigonal pyramidal, and that's because it looks like a pyramid. So if I hold it at right here, you can see that it looks like a pyramid with a triangular base. If I just rotate this around in 3 dimensions so that you can see this. So we're going to do our very best to try and recreate that representation. So again, this time we're going to put our electrons at the top, just like we saw in the initial diagram. So this is what our final picture should look like. In this case, again, because of this pair of electrons on top, we see a slight shrink in the bond angle. So it goes from being 109.5, which is what we would expect it to be, down to about 107 degrees. And there are 3 107-degree bond angles here. Again, you'll have your papers to reference, so you don't have to worry about memorizing the number of bond angles. You'll be able to go back and look at these. In our next example, our last example for tetrahedral, so I'll add tetrahedral once more to the top here, because we have 4 electron domains. This time, you'll notice that we reused the name bent to talk about it. So we have 1 pair of electrons pointing up, 1 pair of electrons pointing down and to the left, and the other 2 are back behind the plane, and this one is coming out of the plane. So we can rotate this however we would like. But it's important to remember that the electron pairs are still taking this tetrahedral shape. It's just where the bonds are actually located that give us the molecular geometry name. So once again, I'm going to use some fast forward action here once I do this to recreate our molecule kind of on this flat space. Once again, we're going to see a contraction because of those pairs of electrons. So this time the new bond angle shrinks all the way to 104.5. Now, because we just have 3 atoms in our entire molecule, we just have 1 bond angle of 104.5. We are now up to our 5 electron domains. So again, for this point in the video, this is only going to be for our honors and our accelerated honors students. So these are examples where we are exceeding the octet. So we're putting more than 4 pairs of electrons around the central atom. This is only available to atoms in the 3rd energy level or below. So 3rd energy level, 4th energy level, 5th energy level, if we're looking at a periodic table. The name of the first one that we're going to see here, and we'll pick this up on the molecular shapes here, is trigonal bipyramidal. So the prefix bi means 2. So we have 2 pyramids with a triangular base. So if you notice, if I turn this just the correct way here, you'll notice one of these pyramids is on top, and then another one of these pyramids is on the bottom. So we have 2 pyramids. They're basically facing each other, almost like if you're used to Stranger Things, this would be the pyramid on top, and this would be the pyramid in the upside down world. So there's a pyramid upside down from where the top one is. So now, a couple of things that I want to mention to you. There are a lot of different bond angles present in this molecule. So first of all, there's a 180-degree bond angle here. If we look at the molecule like this, you'll see there are 120-degree bond angles here, 3 of them. And then of course, if we put this straight up and down again, you'll notice that we have 90-degree bond angles as well. So I'm going to just show all of these. So we have the 90-degree one, we have the 120-degree one, and I don't know if I can get it to show the 181, but there is a 180-degree bond angle between the top atom and the atom that's at the bottom. One of the other names that you might want to know for this is axial and equatorial. So if you imagine the word axial, like the Earth's axis, that's these 2 that are on top and bottom. And then the ones that are along the middle here, So where these 320-degree bond angles are, these are known as equatorial, like the Earth's equator. So we're going to type in the electron domain geometry, trigonal bipyramidal, and trigonal bipyramidal because it's 5 and 5. Now I'm going to fast forward as I make my molecular geometry picture here. So if you notice, looking at my picture, the 3 that are equatorial right here, I'm going to try and just make them a different color for us. The 3 that are equatorial right here are 120 degrees apart from each other. And the 2 that we're going to call the axial positions, like the Earth's axis, so I'm going to make them a different color. We'll make them red. Those are 180 degrees away from each other. So we have 180-degree bond angle, and we have just one of those. We have a 120-degree bond angle. We have 3 of those. And then finally, we have a 90-degree bond angle, and we have 6 of those. So the 90-degree bond angle will form between the atom at the top here, and then each of the ones that are equatorial, that's 3. And then the same thing for the atom at the bottom, and each of the 3 that are equatorial, that's the other 3. Okay, in our next example, we're going to keep our electron domain geometry name the same. So that once again will be trigonal bipyramidal. And the name for our molecular geometry in this case is a rather comical seesaw. So if we look at the molecular shape in 3 dimensions, so you'll see those 2 names here. So the electron domain geometry is trigonal bipyramidal, molecule geometry is seesaw. This is what it looks like initially. So when we make our drawing, I'm going to put that pair of electrons pointing out to the left. But just to show you where that name is coming from, so if I hold it just like this is kind of the fulcrum of the seesaw, and this, imagine, I know this is science humor here, but this is the seesaw part. So if it rocks back and forth along this, with the fulcrum being right here, this is where the name seesaw is coming from. So if you notice, and we're not going to worry about the contraction of bond angles in this case anymore because they get too complicated. But if you notice, we still have 1 of the 120-degree bond angles. That one's right here. We also have 1, 2, 3, 4 of the 90-degree bond angles, and we still have our 180. So I'm going to make that drawing for us. Okay, so here's what our final drawing looks like. Again, I'm just going to color these so that we can kind of trace them throughout our diagrams here. So these 2 represent the only 2 equatorial ones that are left. Remember, there were 3 originally, and the 2 that I'm coloring in red here represent the 2 axial ones. Those are not going to change throughout this entire process as we go from 5 to 4 to 5 to 3 to 5 to 2. So I mentioned this already. So the 180-degree bond angle is still there, and there's 1 of them. Now our 120-degree bond angles have dropped to just 1 of those, which is right here. And finally, the 90-degree bond angles, we now have just 4 of those, down from 6 originally. Okay, in our next example, we still have 5 electron domains, so we're going to keep that trigonal bipyramidal name. And when we look at the molecular geometry in this case, it is called T-shaped. And if you look at the picture, so we're going to put 2 pairs of electrons in the equatorial positions. If you look at the picture, though, it's called T-shaped because, if I can get it to look like it, it looks like a T. So just moving that around, this is called T-shaped planar because they're all in the same plane, as you can see right from that angle. And we're going to draw this so that we have 1 pair of electrons to the left and 1 pair of electrons coming out of the plane of the computer at us. So T-shaped planar, and I'll make my drawing now. Okay, so my drawing is complete. If we look at the bond angles that are left, we still have this bond angle of 180 degrees formed by the two axial position atoms, so the one at the top and the one at the bottom. And we now have just one equatorial atom left, so we lost that 120-degree bond angle entirely, because that's all that needs, at least two atoms in the equatorial position, and now we only have one. So we have one 180-degree bond angle, and as far as the 90-degree bond angles, we only have two of those remaining. Okay, let's take a look at our last example in the trigonal bipyramidal category family here. And this one is going to be called linear. So if we go and take a look at the molecular shape, you'll notice that all of my equatorial atoms have now been replaced by pairs of electrons. So the only thing that I have left is this bond between the two axial atoms and the central atom. So that is a 180-degree bond angle there. So I'll make my drawing real quick. Okay, so looking at the one bond angle that we have here, we have a 180-degree bond angle, and we have just one of them. Okay, we will now look at our final family of electron domains. So we will not go above 6 electron domains. So this is called octahedral, and the name octahedral is coming from an octahedron, which is an 8-sided geometric figure. And again, if we have 6 electron domains and all 6 are bonding, we have an octahedral. So just to take a look at what this looks like. So we have one atom pointing up, we have one atom pointing down, we have 1, 2, 3, 4 atoms that are coplanar here. So these 4 are coplanar. Notice that we have a ton of 90-degree bond angles. So in fact, we have 12 of them, the top with each of the 4 in the middle, the bottom with each of the 4 in the middle, and then 4 more for each of the 4 with each other. So I will go ahead and make my drawing of the geometry. Okay, my drawing for the geometry is now complete. So just a couple of things. In terms of 180-degree bond angles, I have 3 of them. So going back to the molecular shape, I have this one that's from top to bottom. I have this one that's from the back left to the front right. And I have this third one, which is from the front left to the back right. So 3 180-degree bond angles to start off with. And as we mentioned earlier, as far as 90-degree bond angles, we have 12 of them. Looking at our next example, again, we have 6 electron domains, so we're going to keep the octahedral name for the electron domain geometry. And here, the molecular geometry will be called square pyramidal. So if we look at the picture for this, you'll notice that it looks like a pyramid. So each of these 4 atoms coming up to the top would form a pyramid, and it has a square base as opposed to a triangular base. So this pair of electrons down here, if you ignore this and just look at these 5 atoms that are at the top here, you'll see where that name square pyramid comes from. So now I'm going to build that molecule so that we could see that here. So here is our picture for the square pyramidal. In this case, we still have 2 out of our 3 180-degree bond angles. We lost the one that was going from top to bottom. So we have 2 of those, and our 90-degree bond angles have been reduced to 8 because we lost all of the ones that could form with the atom on the bottom. Okay, our next example is called octahedral again. But this time, we're going to remove the atom that is opposite the pair of electrons, and that will leave us with a shape which we're going to call square planar. So if I show you what that shape looks like on the screen, you'll notice we keep our square here, and they are in fact all coplanar with each other, so thus the name square planar. Notice that our original pair of electrons here, that new pair of electrons is opposite that first pair. So this is what it looks like in 3 dimensions. It's kind of cool looking. Okay, so I'm going to make the geometry drawing over here. Okay, so this is what our final geometry looks like. And if you are experiencing trouble as I am moving these letters around, I know it can be frustrating, but I do really appreciate you going forward with this. So we have 180-degree bond angle. We still have 2 of those left. And our 90-degree bond angles have now been reduced to just 4. Those are the 4 here. So 1, 2, 3, and 4. And this is what our picture for square planar will look like. So our next example, we have an octahedral. Once again, that part will not change going forward. And this time we're going to go back to our T-shaped planar name. So we have 6 electron domains, only 3 of which are bonding. So notice that we have that same pair of electrons at the top, pair of electrons at the bottom. Now one of our pairs of electrons of the 4 that were coplanar, one of those atoms has been replaced by a pair of electrons. So we have that right there. So I'll go and make my drawing. So here's what my final drawing looks like. I am now reduced to just one 180-degree bond angle and 2 90-degree bond angles. So this one here and this one here. Remember, all 3 of these B's that are on there are in those equatorial positions and they're coplanar. Okay, we have reached our last example. So this once again will be octahedral. Our molecular geometry this time will go back to being called linear. So I'm going to make my drawing in just 1 second. So just to show you why it's called linear, you'll see this one bond angle of 180 degrees that remains here between the atom that is in the back left and this atom over here in the front right. So I'll make my drawing based on that. So here's my final picture. This BAB is the only bond angle that we have left, and that is 180 degrees, and there's just one of those. If you've made it this far, congratulations. Thank you for hanging in there as we went through this rather complicated process. The good news is that you'll be able to use this chart on any assessments that you take as a reference, so you don't have to go and memorize bond angles and how many of them there are. In our next lesson, we'll actually take this and then apply it to some real-life molecules to try and figure out what they look like. Thanks very much, everyone. Have a great day.